Welcome to the High Energy Density Science Center Seminar Series. I'm pleased to have with us today Professor Foulkes, who is Professor of Physics at Imperial College London. Professor Foulkes received his PhD at Cambridge before going off to Bell Labs and then winding up at Imperial College. His research interests are in using quantum Monte Carlo techniques and in extending the quantum mechanical approaches used to study solids beyond the Born-Oppenheimer approximation, taking proper account of the exchange of energy between spins, electrons, and ions. And I would like to note that this talk will be recorded, so if you're uncomfortable with that, please sign off. And also it's an unclassified talk, so keep discussions unclassified, and also we have visitors from outside of the lab as well. Otherwise, I'm very much enjoying hearing his talk and solving the many-electron Schrödinger equation with deep neural networks. And please take it away.
Thank you very much for the kind introduction, and thank you very much for inviting me to talk. I hope you can all see my screen. Let me know if you can't. I suspect I was invited to talk here because a few years ago I did some work on the warm dense electron gas, which is, I guess, closer to most of your interests. That was fun work. We got together with a German group of Michael Bonnets from Kiel, and we kind of invented several newish Monte Carlo methods to try to calculate the exchange correlation energy of the warm dense electron gas, which, as I suspect most of you know, is the main ingredient that goes into constructing most of the density functionals for Mermin finite temperature density functional theory, which is quite widely used to simulate warm dense matter already. That work was kind of interesting, but I know that Fionn Malone is currently in your quantum simulations group, and he was my PhD student at the time. So I guess you have all heard about it way too much. And also I haven't done much on it for the last couple of years. I have started now revisiting it, and we're trying to extend the methods we developed now to look at real materials, so real atoms in boxes, not just electron gases. And we just have some very preliminary data, but we're not ready to talk about that yet. So instead, I'm going to talk about something that may not be too close to your interests, but it's methodologically interesting, and I think it might be actually a really useful piece of work. And it started about a little more than 2 years ago, when these three people, David Fowle, James Spencer, and Alex Matthews, who all work at DeepMind in London, contacted me because they were interested in trying to solve the many-electron Schrödinger equation with deep neural networks. And really what they wanted to do was quantum chemistry with neural networks. They approached me because I know about quantum Monte Carlo methods, and because James Spencer is somebody I've worked with in the past before he was at DeepMind. And DeepMind, as you probably know, is a very strange place. It was a startup founded by a few academics from University College London, and it's still in London. There's an office in St Pancras with several hundred PhDs all beavering away on deep learning. It was then acquired by Google, and they're the company responsible for AlphaGo, the neural network that beat the world Go champion, AlphaZero, which is in some ways even more impressive. They trained the neural network to play itself at chess, giving it only the rules of chess, nothing more. And after a few hours playing itself, it developed strategies that enabled it to beat most of the world's other chess engines that had been under development for decades. They've also started a science team now, and quite recently you may have read some publicity about them at least making progress in the problem of protein folding. There are a lot of overblown headlines about them solving it. No, they haven't solved it. They're just doing it better than other people, again with deep learning. So they are really good at this stuff. I'm not. I know very little about it still. Working with them was fun, but a bit weird. They're a very secretive organization, and I had to, they wouldn't let me just collaborate with them in the way I would with another university professor somewhere. They made me sign on as a consultant so that they could control me and make me sign an NDA. And for the first year and a half of this work, I wasn't even able to see any of the code they wrote. It was all very peculiar. I'm not used to working in that way. Maybe in Livermore some of you are. The code is now open source, all except one function really. So you can see it. You can find it on GitHub if you want to. And So I now have seen the code, and I have some PhD students just starting working with it. But this work was essentially done, all of the hard lifting, the people in DeepMind, and I just provided wisdom of the kind. It's fun anyway. The other thing I should say is that when they came to me, I was very skeptical about deep learning. I'd heard about it. I thought it was vastly overblown, overhyped, and all it was is function fitting. All it is function fitting. I still think that, even after having worked with them, but I have come to realize that it's a really, really good kind of function fitting, way better than ordinary function fitting. So yes, it is kind of just function fitting really, but it's a very effective kind. So I didn't know quite what the audience would be like here, so a lot of this talk is quite introductory. I hope that's okay. In particular, I wanted to introduce the problem because it's quite far away from high energy density physics. I do think, however, that many of the techniques I'm developing here could be used in other contexts. You know, not exactly the same, but the same sorts of approaches. So I might get back to that a little bit later. So suppose you wanted to do chemistry in a computer. That's always been my dream. It may be an unrealizable dream, but it's certainly a dream. One of the issues with it is you need very, very high accuracy. Chemists talk about, I'm not a chemist, I'm a physicist, but they talk about 1 kilocalorie per mole, which in our language is 43 milli-electron volts per particle. When I used to not really understand why you need this accuracy, but actually it's pretty obvious. It's at room temperature, KT is 25 milli-electron volts, which is a very small number, even smaller than 43. And the energy differences between competing structures can be even smaller than that. I've worked quite a bit on solid hydrogen. This is low temperature solid hydrogen. And the energy differences between competing phases can be, tens of milli-electron volts per atom. And then if you want to do strongly correlated systems or magnetism, when you're down at much lower temperatures, and after phase transitions that happen at a few degrees Kelvin, you're down at even smaller energy scale. So yes, if you want to do quantitative chemistry in a computer, I'm afraid you need at least chemical accuracy. That's the bad news. The good news is we know what equation we want to solve. It's the Schrödinger equation. We know that for almost all circumstances, it's a very good approximation to treat the atoms as classical. And so we just put them at positions di. And then we need to diagonalize this Hamiltonian. And in particular, what we need is the ground state energy as a function of the ionic positions. If we knew that, we could simply use Newtonian mechanics to follow how the nuclei moved around, and all of the chemistry would be done. Because if we could solve this equation properly, the chemistry is correct. And we know that. I mean, it really is. In those cases when you can solve it accurately, the chemistry is right. So if you look around the room you're sitting in at the moment, almost everything in it is really built into this equation. It is, in a sense, a grand unified theory. And it shows you, in a way, how useless grand unified theories are. They don't gain you as much as you might hope. It's nice to know you have it, but it's a very hard thing to deal with. And in particular, the Schrödinger equation is believed to be NP hard. There are papers purporting to prove that, quite convincing, I think. And so the best we can realistically hope for are good approximate results. There's another issue about energy and length scales. I've already talked about energy scales. These are similar ones, same sorts of numbers I've talked about before. What's less often remarked is that if you want a small energy scale, say 10 to the minus 1 eV, that corresponds to a long length scale, just from particle in a box kind of problems, really. So for example, let's say we want 0.1 eV and we say that the Fermi energy of our material is 10 eV. These are just ballpark numbers. Then E over E Fermi is 10 to the minus 2. And since energy is half h bar squared k squared over 2m, which is 1 over wavelength, proportional to 1 over wavelength squared, that gives you lambda over the Fermi wavelength is about 10. And putting in a plausible Fermi wavelength, you get a length scale of about 20 angstroms. So you need quite a big box of atoms in order to get accuracies down at this kind of level. So not only do you have to simulate atoms very accurately, simulate materials very accurately, but you need to be able to simulate quite big boxes of them. And given that the problem is NP hard, that's a real challenge. I should also point out that the natural energy scale in the Schrödinger equation is the Hartree, 27.2 eV. That's the atomic unit of energy. Or another way to say it is that the energy of an electron in a heavy atom might even be thousands of eV or more. So these are, unfortunately, the Schrödinger equation is too high an energy theory for us, really. If we want to do chemistry, we want to be down at these length scales, energy scales. We don't want to be solving an equation that produces answers in the order of 10,000 eV or something. Unfortunately, we don't, at the moment, have an alternative. There are, of course, low energy field theories that describe things very close to the Fermi energy and are used in many body theory a lot, but we don't have an intermediate theory, a lower energy theory that really works in a systematic and general way for quantum chemistry. So we're sort of stuck with the Schrödinger equation, and it will be a hard problem to solve. What have we got? We've got density functional theory and, of course, thermal density functional theory in warm dense matter. And that can sometimes actually achieve chemical accuracy if you tune the functional carefully, but it doesn't tell you the right functional to use. And within it, there is no way to tell whether you've got a good result or not. And there's no way to improve your functional built into density functional theory. You need to do that from outside. So it's quite limited, but it's certainly useful. And in fact, it's remarkably amazing how well it works, given that it's really in form a mean field theory. I suspect that part of that is that at low temperatures, many weakly correlated materials have nearly non-interacting quasi-particles in them. And I've always wondered whether in very hot systems, the thermal density functional theory is actually so good. And one of the things I'm trying to do with this quantum Monte Carlo project that I'm not going to talk about, the warm dense matter one, is hoping to benchmark density functional theory in warm systems. Anyway, we're talking about cold things here, really cold. You can do perturbation theory. It works really quite well for weakly correlated materials. But of course, it relies on perturbation theory from a non-interacting or at least Fermi liquid state. And what are you going to do if you've got strong correlations or non-Fermi liquid ground states and there's a phase transition between the non-interacting system and your one? The method I'm going to talk about today is the silliest of them all. It's to guess the wave function. Doesn't sound very promising, but it was the method responsible for most of our being humankind's few successes in understanding strongly correlated non-Fermi liquid systems. Okay, BCS maybe isn't strongly correlated, but it's not you can't get it from simple Fermi liquids. You need to add extra interactions and go through a phase transition. And it was solved by guessing the wave function. The fractional quantum Hall effect was solved by Bob Laughlin sitting down and somehow magically plucking the wave function out of thin air. There's the beta ansatz. There are a few others. So it's not a useless method, but it does seem rather limited. There's a long history in computational electronic structure theory of parameterized wave function guessing, which is in fact where my work fits in. So Hartree-Fock theory is really just saying, let's guess that the wave function is a determinant. The configuration interaction method, beloved by some quantum chemists anyway, is just saying, let's guess that the wave function is a linear combination of determinants. I'll talk about Slater-Jastrow in a minute. The coupled cluster wave function is a slightly cleverer guess where you start with the determinant and then act on it with an operator that improves it and adjust the operator to make it better. And there are a bunch of others. More recently, I suppose, in many body theory, tensor product and matrix product states have been widely used. They're just really another guess. So a lot of what you see in computational physics is actually, computational quantum theory is actually done this way, whether it seems silly or not. So what I'm going to be talking about today is variational Monte Carlo, which is one of these methods. You guess the wave function, and it's a many-particle wave function, so it's a function of n electrons. We're currently going up to about 60. With other variational Monte Carlo methods, you can go up to about 1,000, so that's where we would like to get, and we might be able to get, I'm not sure yet. I'm suppressing spin just to make things look easier, but it's there really, of course. Once you've guessed the wave function, you just evaluate the energy expectation value, which requires doing an integral. So if we have 30 electrons, this is a 90-dimensional integral, plus a spin sum. And the way you do it in Monte Carlo methods is you turn it into a Monte Carlo integration. So all I've done is I've taken this equation and multiplied and divided by psi trial, our guessed wave function. So out front I have a psi trial star, which I moved here. And I also have h psi trial divided by psi trial. And this looks like now a statistical thing. So psi trial squared is the probability of having electron 1 at R1 and electron 2 at R2 and so on. And this is the volume element they're sitting in. So this is a probability of sampling the electrons in a particular configuration. And this is a score when you sample them there. So if you were able to throw darts into your configuration space, your 90-dimensional space, such that they landed according to this probability density, this would be just the average score scored by those darts. And that's literally all Monte Carlo integration is. You throw darts and you average the scores, which are this thing we call the local energy. And there's a lovely algorithm for throwing the darts, the Metropolis algorithm, which I think may have been invented at Livermore, I'm not sure, certainly somewhere in an American national lab. And it just works, so we can do it. And the nice thing about this method is the error in the integral decays like 1 over the square root of the number of darts you've thrown, independent of dimension, whereas all grid-based methods become worse and worse in higher dimensions. And then you just adjust your guess to minimize the energy. So it's a very, very simple idea in principle. The most common guess for large three-dimensional systems is still what's called a Slater-Jastrow wave function, which is a very crude one. You start with a determinant. Typically, these would be DFT orbitals or Hartree-Fock orbitals. That's quite good at keeping electrons of the same spin apart, because if two electrons of the same spin approach each other, if R1 approaches R2, these two columns become the same. If they have different spins, however, these two columns don't become the same, because there's really a spin part in these wave functions too, and they get together, they get too close together. They don't like that because of the Coulomb repulsion. So this term out front, called the Jastrow factor, is designed to help fix that, and it pushes electrons apart when they get too close together. So it's a crude guess, but it works really quite well in weakly correlated Fermi liquid-like solids. And it's very good for scaling. You can easily get up to the size of system you need to get good results. One of the things you can do with Monte Carlo methods, it's just time for a picture, I thought, is calculate pair correlation functions of electrons, which you can't do in DFT because they've been lost. And this was a calculation I did many years ago with a postdoc called Maziar Nekovi, where we were looking at a system with a periodic sine-like potential applied to it. So it's a 3D system, but the potential is just in one dimension. And this is a picture of the electron density in that one dimension, this ribbon. And we froze one electron in the low density region here. And around any electron in a solid, there's a thing called the exchange correlation hole, which is a kind of exclusion zone within which other electrons don't often come. And they're kept away both by the Pauli principle and, of course, by Coulomb repulsion. And there's a sum rule on that hole that it integrates up to -1 electron, so an absence of 1 electron. And so this is the hole in our Monte Carlo simulation. And you can see that we can't really scoop out a hole around the electron at the bottom here because there's no other electrons there to remove. And so the hole ends up on the high density regions on either side. It's a bit like an image charge if you bring a charge outside a metal. The one on the right-hand side is what you would assume in the local density approximation, where you would take this electron in a low density region and pretend that it was in a uniform electron gas of that low density. And so in order to hold one electron, the hole has to become enormous there. So this just shows that sometimes things like the local density approximation are very wrong, but mainly it's there just because it's quite pretty. What are the limitations of this approach? It's one of those approaches that's garbage in, garbage out. You just put it in, you guess the wave function, very brittle, that kind of approach. It's not normally capable of chemical accuracy, even in weakly correlated systems. You can use these VMC functions as a starting point for more sophisticated methods, such as auxiliary field Monte Carlo, which I know you do a lot of in your quantum simulations group, and they work much better. And the other thing is it tells you, like DFT really, it doesn't tell you what to do when it doesn't work. You could try linear combinations of determinants, but the number you need increases exponentially with system size generally. And so it's really no help when you don't understand the physics. And most of the interesting questions in solid state physics, in my view, are about when we don't understand it, when the non-interacting picture we rely on so much breaks down. So let's now get to the work we did. We started off from two observations, which I think were not really mine. I think they were mainly the deep mind guys' ideas, but they are good ideas. The first one is that artificial neural networks are flexible and efficient function approximators. That one I had to be convinced about, but I'm now utterly convinced they really are. And so perhaps instead of trying to write down a formula for the wave function, which is hard to do because you have to guess it, we'll just represent the wave function as a neural network. So the way you remember, a neural network is essentially just a computational architecture where you feed in some numbers and out comes another number. So it is nothing more than a function, really. It evaluates a function. What function it evaluates depends on all the connections within the neural network, all the weights associated with those connections. So if you can adjust those weights, you can approximate different functions, and that's essentially what they do. So perhaps we can adjust the weights to approximate a wave function. That was the idea. The other one was cleverer in a way, but building on work of other people. And it was the observation that nothing requires the orbitals in a slated determinant, here is one, to be functions of the coordinates of a single electron. Okay? All we actually need is that we want to create something antisymmetric because it's got to be a fermion wave function. And so that's the only hard requirement, is the antisymmetry. And so you can do that with more general determinant-like things. And in particular, you can take those one electron functions and replace them by a function like this. So it's a so just as in the ordinary slated determinant, we would have a function psi I of an electron coordinate rj. But now we've made it depend on all the other electron coordinates too, in a general way that will be built into our neural network, parameterized in our neural network. And that is tedious to write, so I've got a shorthand notation. This is rj and the set of r's not equal to j. And as long as the dependence on the set of r's not equal to j is completely symmetric, not antisymmetric. In other words, if I flip, say, if j is 1 and I flip r2 and r17, the wave function this function doesn't change. We can build a determinant out of these functions, and it's still antisymmetric. Okay, so let's look at that. Let's just look at the first two columns here. Suppose I flip r1 and r2. Well, this becomes psi 1 of r2, and this becomes psi 1, and this becomes psi 1 of r1. I flipped r1 and r2 around. I also have to flip inside this squiggly bracket r1 and r2. Well, there isn't an r1 here, but there is an r2, so that the r2 in here becomes an r1, and the r1 in here becomes an r2. Now, because the order doesn't matter inside the squiggly brackets, I've literally just flipped this function with this one. So it works just like a slated determinant, and if I flip two electrons around, I interchange two columns. This is not a new idea. It's a generalization of what's called backflow, which is an idea, I think, due to Richard Feynman a long time ago in work on liquid helium. And his idea was that instead of a function of R1, it's still a function of just one three-dimensional variable, his orbitals here. But that one three-dimensional variable can itself depend on the positions of the other electrons. So it can get slightly moved around depending on where the other electrons are. So we're going way beyond that by actually having a function of all three n variables here, if n is the number of electrons. There's also a guy called Brian Clark from Illinois who's applied quite similar ideas, a bit more limited, to look at lattice models. So that was also a precursor to this work. And the main thing we did actually was to make a neural network that builds functions like the ones inside this determinant. And then the last layer of our neural network evaluates the determinant from those functions. So that's essentially what we did. So I wanted to do a little, I'm no expert on neural networks. In fact, I know very little about them. And there are probably people in the audience who know a lot more than me. But I wanted to at least explain what they are, because they're not magic. And there's a few very clever ideas in there. So I'm going to go on a little diversion for about 10 minutes on neural networks now, maybe less. So here's a very simple neural network. We have four inputs, these, whatever they are, four numbers go in, and in this case, one number comes out. The network itself is a computing it's actually really implemented primarily in software, and we run it on GPUs. But we can think of it as a piece of hardware if you want. And it's got a bunch of neurons, which are the blue circles and the turquoise circles here. And the inputs from the first layer are passed on to the second layer by all these arrows. And all these arrows represent is a matrix. So for example, the input to this neuron is some linear combination of the 4 inputs defined by the 4 arrows. So what we've then described is a linear mapping from these 4 numbers onto these 5 numbers. The matrix doesn't have to be square. So that's what I've written here. XL are the inputs or the values of the 4 neurons at level L, or 5 neurons at this level if you want. And W is the matrix that maps those the values of those neurons onto the values at the next layer. And all a neural network is we pass on these values from layer to layer until we eventually create an output from them, again, with just a linear transformation. Now, if it were only linear, a composition of linear transformations is, of course, just another linear transformation, and it wouldn't be very interesting because it would be very limited as to the functions it can represent. And so the one other trick you do is that once you've added up the 4 inputs here to figure out what this neuron is going to do, you apply a nonlinear function to them, which I've called A here. And this was modeled on the idea of what happens in a human brain. So in a human brain, if a neuron has very little input, it essentially doesn't fire. And as the input passes a certain threshold, it begins to fire and switches on, essentially. So the function goes up and is 0 when the input is small and 1 when the input is big. You can use something like a tanh function. We need to take great care in this that everything is differentiable and smooth. So in fact, we do use tanh functions. And that's it. That's all a neural network is. There are theorems that say if you have a big enough neural network, you can approximate any function with it very accurately. Why is it of interest? It's of interest. In the early days, they were invented a long time ago. The whole idea goes back to the 50s, but it never really caught on until the 90s, I think. When first of all, computing hardware got better, and also it was realized how you could learn the parameters, all the matrix elements here of the W's and these shifts, the biases that you can also add, very efficiently. So if you know what the output ought to be, you can work out all the parameters of the neural network very efficiently to try and optimize towards that output. So you get very, very efficient algorithms for optimizing your function, if you want. And they're based on what's called automatic differentiation and backpropagation, which I'm going to very briefly explain, just because I personally find it fascinating. And when I first learned about it a few years ago, it sort of warped my brain in a way I enjoyed, and made me think about computation in a slightly different way. So before we go on to that, the only difference in our work is that the inputs are electron positions and the output is the wave function. So numerical differentiation. If you want to optimize a function, you need to really work out how does the function change if you change the parameters that define it. So you want derivatives of the output with respect to parameters of the function. Or equally, another common use case is derivatives of the output with respect to values of the inputs. The natural way to do that is with finite. Of course, mathematics can do this symbolically, but that's a rather limited technique, and most of the functions we compute are way too complicated for that. So the next approach that people used until quite recently is just numerical differentiation, finite differencing. That, of course, is problematic. If your delta x is too big, the approximation to the derivative is just inaccurate. But if it's too small, the evaluation of the numerator here is very difficult because you're taking one large number away from another to get a very small number, and you're swamped by rounding error. So that's one reason this is a bad way to do it. Another one is that the amount of work you have to do scales linearly in the number of derivatives you want. And if we actually have thousands of inputs, or many hundreds of inputs anyway, not quite just the electron positions, we also use differences of electron positions. And so we would that would cost us thousands of times the computer time just to evaluate all the finite differences with respect to each displacement we could make. Automatic differentiation is the solution to this problem, and I really now convinced that it is, in many cases anyway. And all it is really the chain rule that you all learned as first-year undergraduates. any function that computers can evaluate is a simple thing. It can do, you know, adding and subtracting and dividing. You can probably include cosines and sines and a few simple power functions and things built into your standard library, but they're all very, very simple things. The basic steps of computer programs are simple because computers are simple. And you can therefore decompose your computed function into a sequential list of essentially arithmetical operations, each of which is easily differentiable analytically. And by doing this, as I'll explain in a sec, we can get derivatives with numerical precision, and we can get all of them at a cost which is only a bit more than one evaluation of the function. So here's a nice simple example. This was invented by one of my PhD students, and I think he got it out of a book, but it's a nice way of explaining it. So here's a very simple computer program. We take three inputs, x1, x2, and x3. We evaluate a new number called y1, which is here, x1 squared plus x2 squared, and we're not going to need x2 anymore, so I'm going to forget it and just keep y1 and x3. We now evaluate a new number y2, which is given by this formula, just a random choice. And then we're only interested in y1 and y2, which are our two outputs. Now let's imagine working out a differential version of this program. This is with the mathematics, so it's not with small numbers, it's mathematics. Just differentiating this, dy1 is 2x1 dx1 plus 2x2 dx2, and dy2 is, well, whatever it is, there's the formula, you all know how to do that. Now let's look at this first step. This is of course linear. dy1 is a linear function of dx1 and dx2. These coefficients here may be nonlinear, like e to the x3 here, but they depend on the numbers x1 for which we're trying to evaluate the program. So yes, if we're trying to evaluate the program with a specific set of inputs, we'll get different numbers here. But given those numbers, the link between the dy's and the dx's is linear and can be represented as a matrix here. In this case, it's a 2 by 3 matrix. If you apply this 2 by 3 matrix to the column vector of the dx's, you get the column vector of the dy's. The second stage is exactly the same. So, and it's this case a 2 by 2 matrix. So we now have a formula that links the two variables after one step with a matrix to the three variables you put in. And the two variables that come out, these are the outputs, are given by another matrix times the middle stage values of the dy's. And hence, the whole thing is a matrix times the dx's. And so this matrix, all the things in these matrices are just numbers for a particular run of your program. And you're already evaluating them. But this product of two matrices is in fact therefore the Jacobian, because dy1 is dy1 by dx1 dx1 and so on, plus dy1 by dx2 dx2. So by doing this accumulation of matrices and multiplying them together, we can find the Jacobian of our program, if you want. And this is not approximate. We're not relying on small dx's here. How do we use this? Well, this is the Jacobian we found. So if we were to apply that Jacobian, for example, to the vector 1, 0, 0, we would get the derivative of the two outputs with respect to the one input, dx1. And that's the first thing you might... So that gets you the derivatives of all outputs with respect to one input. If your program has a few inputs and lots of outputs, that's great. And you can just do it that way. Our program has a lot of inputs, hundreds of them, but just one output. And so we would need to put 100 different vectors in to get all of the 100 different derivatives. However, you can do this backwards. If you take the same matrices, and instead of post-multiplying by a column vector, you pre-multiply by a row vector, and you work out what you get, remembering that the product of these two matrices is the Jacobian, you get a row vector whose elements are the derivatives of the output 1, because I chose 1, 0 here, with respect to all the inputs. And so that's essentially the only nasty part of this is you have, as you go through the program forward, you have to accumulate these matrices in order, or at least the important elements of them, and then you have to remember them in order to step back through the program and evaluate the derivative of all your one output in our case. There are two here, but your one output with respect to all inputs. And you do it all in one run of this reverse program. So it's surprisingly efficient. So I think I've just said all this. I won't say any more about this bit. If you had infinite RAM, this would be fantastic, because computer scientists tell me that the computational cost is bounded at 5 times the cost of one evaluation of the original function, no matter how many derivatives you want. Unfortunately, there is a cost in RAM, and we do run out of memory, which is what's limiting our system sizes at the moment. So this is actually a fantastic method. And when you apply it to your neural network, there was this clever observation that if you think of a network parameter, that's the strength of one of these these synapses that links to neurons, or in other words, a number in one of these matrices that you apply from layer to layer. You can think of that as just another input to the evaluation of your function. It's just an input that you enter halfway through. And so you can work out derivatives of your wave function with respect to network parameters using this same algorithm, which is why neural networks are so fantastically efficient to optimize relative to, and you can optimize neural networks with hundreds of thousands of parameters. We're doing that, in fact. So here's what we actually do. I may have to rush through some of the results, but I think I'll be okay. We have an input layer, which is, in this case, 4 electrons. We have some hidden layers, not very many of them. I think there's only about 4 typically, and out comes a wave function. How do we know whether our network is a good one? Well, we do variational Monte Carlo. We sample a set of, we start with an initial network, which typically we make look like a Hartree-Fock wave function. We sample a lot of points from that wave function squared using the Metropolis algorithm. This network can evaluate the wave functions, therefore I can sample it. And then we use all those values of the wave function squared to evaluate this integral, or estimate this integral using Monte Carlo integration. This thing, evaluating h on psi, requires derivatives of psi, but they're also generated by the backpropagation, by the automatic differentiation. And we also evaluate derivatives of the energy with respect to the parameters of the network. So we accumulate, we do this for a batch of samples, get a statistical estimate of ET, and then adjust the network following the derivatives, going downhill if you want, to try and minimize the energy. It's that simple. So it's very different from normal machine learning. We're not learning from data. We don't have pictures of cats that we've labeled as cat or dog, cat or not cat. We're learning from the variational principle. We're learning from an equation. I like to call it learning from equations. And if you think about this, it's a very general idea. Vast areas of physics and engineering are formulated variationally. Anytime you have a variational principle, you could do this. And so I think it's actually a general approach. I don't think I'll go into details of what FermiNet looks like. I did want to say a couple of things. I'll just look at this slide. I think it may be too small for you to see anyway. We have a stream for each electron. That's the first thing. So for each electron, we put in various inputs. And those inputs include the separation of that electron from every nucleus. There's a 3D vector for each of those separations. So that's 3n per electron. 3 times the number of nuclei per electron. We also put in not, however, just those vectors, but the moduli of those vectors, the absolute values of those vectors, the separations of the electrons from the nuclei. And there's a good reason for that. If you think about the wave function of a hydrogen atom, it's got a cusp at the origin where the nucleus is. Now, our network is designed to be differentiable, completely differentiable. Everything in it is smooth, and it has great trouble representing cusps. However, the function modulus of R1 minus a nuclear position also has a cusp at the position of the nucleus. Actually, it's a downward cusp, isn't it? It looks like this. So that allows our network to build the cusps it needs out of these cusps we put in. And the network itself remains completely differentiable. And so we're kind of allowing us to represent the cusps between electrons and nuclei without making our network have problems differentiating our network. We also put in separations of pairs of electrons because we want to build in correlations. And again, they're moduli because there are also cusps when electrons approach each other. And as we go through the network, we have such a stream for each one electron. And as we're going through at every layer, we feed in information about all the pairs of electrons and also about from the other one electron streams. And the result is we generate a whole bunch of functions. I'll just say this in words. We generate a bunch of functions like this, which are exactly the kind of things we want. Yeah, they have an electron coordinate and depend in a completely symmetric way, because that's built into the architecture of the network, on the positions of all the other electrons. So our network builds a bunch of these functions from which, in the last step, we just evaluate a determinant. We guide it in no way at all except with antisymmetry and the variational principle. That's it. So we don't have any concept of p orbitals or s orbitals or anything like that. We don't put any other symmetries in. We also generate more of these functions than we need. And when we're trying to build determinants out of them, we just pick a random selection. Sometimes we build multiple determinants and make a linear combination, and then we just pick other random selections. There's no kind of thinking, no chemistry goes into it. I think that's all I needed to say about that. Oh, the other thing is these functions are neither normalized nor orthogonal. It turns out not to matter. I'll leave that. We have a very efficient algorithm for optimizing our network. This is optimizing a network with ADAM, which is a well-known machine learning kind of algorithm. And this is using another one called KFAC, Kronecker factored approximate curvature, which is obviously much better in this case. We don't really understand why. It's an order higher, second order, but it's not normally so much better. This algorithm that we're using, KFAC, is actually very similar to stochastic reconfiguration invented in physics by Sandro Sorella, and they were invented within a year of each other. KFAC came just before, but I never knew that until we got into this work. This is a little movie of the network learning. It's not a very good movie. It doesn't show you much, but it's an ethene molecule, and these are just snapshots of the electron positions as we go through learning. And if you look very, very carefully, you can see as the movie progresses, the number of electrons are sort of around the nuclei is increasing. You can only see the 2 carbon nuclei here because the hydrogen ones are so negligible. So I don't think it's a very interesting movie, but it's the only one I had. So let's look at some results. So here we are just looking at conventional methods. So this is not FermiNet, not our method. This is a conventional variational Monte Carlo calculation done with a Slater-Jastrow wave function. It was done very, very well. I know it's quite old now, but Priyanka Seth spent a whole PhD struggling with this and did a job that was very, very good for its time and is still good, using just one determinant here. And this little gray bar at the bottom is chemical accuracy. These are just first row atoms. We also did a Slater-Jastrow wave function, but we did it with a neural network. So we built a neural network that represents a Slater-Jastrow wave function, and we were able to beat Priyanka, but not by very much. It just shows that she did a good job, but neural networks are particularly flexible function approximators. There's also the backflow idea that I explained briefly earlier that goes back to Feynman. Priyanka did some backflow calculations, and we did a neural network backflow, which again beats the conventional one slightly, but is qualitatively the same. And this is a one FermiNet determinant, no fiddling or anything. It's actually much easier to do than the others, much easier to optimize. We're still not quite at chemical accuracy with one determinant, but we're at least a factor of 8 down on original single Slater-Jastrow. If we use a few determinants, I probably haven't got this data for atoms, but I've got it for other things here. We can get within chemical accuracy for all of these atoms. And we don't seem to need a lot. We've never used more than 16 determinants, and we can get quite big molecules really very well that way. This is, in fact, what happens when you add more determinants. So this is the number of our determinants. They're not really Slater determinants. As you go along the x-axis, this is the error in the energy. This little tiny gray bar is chemical accuracy. So there are different methods here. There are two molecules, carbon monoxide and nitrogen. Nitrogen is orange. Carbon monoxide is this bluey green. Nitrogen is often considered a hard one by chemists, although it seems surprising to me as a physicist. This is Slater-Jastrow. This is Slater-Jastrow backflow, and this is FermiNet. So we're getting consistently better, but we're still not quite there, I would say, for these molecules. You might say that doesn't look maybe very impressive, but it looks much more impressive when you compare it with what other people can do. So here we've got 16 FermiNet determinants, and I cannot remember which example this was. Oh, these are the atoms again, with 16 determinants. FermiNet is the greenish one. These are other methods we use. So variational Monte Carlo, which I talked about with a Slater-Jastrow wave function. But this was not done by us. This was again done by Priyanka, I think. And she used up to 100 what are called configuration state functions, which maps onto maybe thousands of slated determinants here. So even with thousands of slated determinants, this was her results. We use 16, and we're way better than that. This is coupled cluster with singles and doubles, and this is coupled cluster with singles, doubles, and triples, the orange one. That's what quantum chemists regard as their favorite method that scales to bigger systems. They don't have many methods that scale to bigger systems other than this and DFT and Hartree-Fock, but this is the best of them. And we're beating that too, even for atoms, where it's supposed to be very good. We can take away electrons and add electrons. These, again, are just for single atoms. The error bars look quite big here, but actually this is way smaller than chemical accuracy. I can't remember what chemical accuracy is, but I think these are all within chemical accuracy. So we can do electron affinities and ionization potentials really quite well. I wanted to show that we can learn the exchange correlation hole and indeed the cusps. So look at the cusps here coming out. This is just pictures of the hole. You can see the cusp there as well. So that was nice. And in fact, learning the cusps is interesting. There's a very mathematical precise result that says that as an electron approaches the nucleus, this was for a helium atom, the derivative of the log of the wave function, modulus of the wave function with respect to its distance from the nucleus should tend to -2. After our optimization, we got -1.9979. There's a similar relation for when pairs of electrons approach, and it should be 0.5 in that case. So we actually do learn the cusps as well. We don't put them in. Probably we should. If we get rid of the cusps, I don't really want to show the picture, but everything gets way worse. So that means getting rid of the modulus of Rij's and trying to let the network do its best. Things get much, much worse. So our error goes from 1.2 to 90 millihartrees. We can do molecules, and we've gone up to a bit bigger than this now, but this data was from the paper we published. I'm still under NDA on some things. Bicyclobutane has 30 electrons, I think, and these are smaller ones down here. This is Ferminet. You can see that it's pretty good. The error is rising as the molecule gets bigger, but if you divide the error by the number of electrons to get this kind of relative error, it's barely rising at all. These are all different kinds of coupled cluster. We worked really hard on them. We did extrapolations to the complete basis set limit, and we did our best. We're clearly doing better than it, and we're much smoother than it too, which is also nice. So this is also very promising. We're close to chemical accuracy per atom. And the other thing I wanted to say is all these molecules were done with exactly the same network architecture. We, of course, re-optimized the parameters, but we didn't change the size or anything. It was all done with the same network. This is nitrogen dimer being ripped apart. It's considered a hard one by chemists. Most methods seem to do quite well, but when you zoom in on them, they don't do so well. And this is just to show that we do as well as anything, really. This is unrestricted coupled cluster, this blue one. I'm not sure what R12 MR ACPF stands for, but it's supposed to be good. So we can do that too. We looked at the H10 molecule because there was a benchmark paper in which everybody who does anything on quantum chemistry for real systems tried their best. Many body physicists as well joined in, and practically every known method was applied to the hydrogen 10 chain. They all seem to do very well, but if you zoom in on the errors, they don't all do so well. This green strip here is where the writers of the paper think the right answer lies. The only thing we did to their data was add the gold curve, which is our Ferminet data. And it's actually handily beating almost everything. And the nice thing is it's a simple method. It's variational Monte Carlo. You can do anything with it. You can calculate anything with it. It's so much easier than the methods we're fighting here. Yeah, I'll leave this out. So let's finish, because my time is up, with a little bit of outlook and sort of critical judgment. Let's start with the positives. Ferminet is way better than any other kind of variational Monte Carlo applicable to molecules with more than a couple of atoms that I know about. I mean, it's just more efficient. We can get better results with much less effort. It rivals coupled cluster, which chemists think is the best method they have for scaling to larger systems, for equilibrium geometries. and it's better than coupled cluster when you have lots of multi-determinant nature, when coupled cluster is known to struggle. It can serve as a trial function for diffusion Monte Carlo and other projector methods. We've just begun trying this, and the results, we've only got one molecule so far, but the results of that were very good. I think it was ethene, and it was much better than other ways of doing DMC. So that's a nice thing too. And the other thing is we've done all this with three guys working, only really two are working on this mainly for about a year. And the methods we're fighting have been in development, many of them for 50 years, literally 50 years. What about questions? How general is the Fermi-net wave function? Is it actually one of these Fermi-net determinants enough? Well, we have a kind of a proof, which I'm never sure I believe because it's very abstract and a bit weird. But it says that in principle, we think one Fermi-net determinant is sufficient to describe any many-particle wave function, any many-fermion wave function. I'm still a bit unsure about that, actually, but because in practice, we seem to need a few. Is a few enough? In other words, if we scale the system up, will we need more? We don't really know. I'm hoping we don't. Even if we do, however, one of our Fermi-net determinants is so much better than one Slater determinant that we can improve trial wave functions used in auxiliary field and diffusion Monte Carlo calculations, I think. What are the limits to accuracy? What is it that's stopping us getting perfect results if this supposed theorem is actually right? Can we do solids? Well, we're coding it up now. And we're trying to just do the electron gas first. We think we can. We know how, in principle. Is the method size extensive? If we scale up the system, will the results be linearly proportional to the system size? Will the energies scale linearly with system size? It's an open question. So variational Monte Carlo where the Slater-Jastrow wave function is, but multi-determinant methods where you rely on having more determinants as the system gets bigger are not. I think we can do size extensive calculations by restricting ourselves to a single Fermi-net determinant, but it would be nice if we could do better than that. How does it scale with system size? The compute time isn't very bad, but we are having trouble with memory at the moment, and that's the bottleneck. So if we can overcome those, we can do the same kind of systems that you can do with standard VMC, thousands of electrons. I see no reason why not. But the memory issue is problematic, I have to say. So that's all I wanted to say. Thank you for listening.
Thank you very much. That was a great talk. So if you have any questions, please enter them in the chat field, and I'll read them out. And in the meantime, please unmute yourself so we can give Dr. Foulkes a nice round of applause.
Figure out how to see the chat field. I've never used this thing before, so you'll have to read them out to me.
Yeah, I'm happy to read them out.
Okay.
There's a question from Vincenzo Lordi. You already mentioned briefly, but can you elaborate a bit on the prospects for solid state?
Doing this for a solid is not more difficult. We essentially what we're doing at the moment, well, maybe I shouldn't say very much. We're putting in, I'll say a bit. Instead of putting in, we're putting in periodic functions of the electron positions to ensure the periodicity around the unit cell, and we know how to do all the standard techniques you use for solids like twist averaging. If the method scales to larger system sizes, I see no problem with doing solids. It's just that we don't know really how far we can scale it yet. In order to get useful results for solids, I think we need to be able to do of order a minimum 100 electrons. I'm pretty confident we can get that far, but I really don't expect any new problems to arise in solids beyond the ones we've already seen.
There's a question from Phil Stern. What are the prospects for extending the method to higher temperature and higher Z, for example, gold?
Yeah, higher temperature would be fun. So you have variational principles. So a method like this needs a variational principle. So you do have variational principles for the density matrix, which is, I guess, what you would need at higher temperature. I've thought a little bit about this. But they're a bit hard to evaluate because they involve trace of rho log rho. So the answer is, at the moment, I'm not sure, not certain. But anytime you have a variational principle where you can formulate it and evaluate something like a local energy, you can do, you have essentially a Monte Carlo integral with a local energy equivalent that you can evaluate. You ought to be able to do something very similar. So it's hard to answer because I haven't thought it very seriously, but at the moment I don't really know how to do it, but it doesn't mean it can't be done.
There's a question from Shuxing Hu. For the molecule case, it looks like the accuracy starts dropping at certain size of molecules. Any reason for that?
So it does start dropping, but the accuracies we were showing were not calculated per atom, but calculated for the whole molecule. Whereas that little grey bar that was chemical accuracy was saying you've got to get that accuracy for the whole molecule. So if you look at our results with accuracy per atom rather than accuracy per molecule, which is a fairer, well, from a solid state physics point of view, is a fairer way of thinking about it, it looks much less bad. It's just a bigger system has more degrees of freedom and the wave function gets more complicated, there's more to approximate. So yes, it will be harder. But if we can keep our accuracy per atom down to a reasonable value as we scale the system, I think that's enough for us. So it doesn't worry me too much because, for example, if I just take a big lump of solid and I just move two atoms around relative to each other, I'm interested in the forces between them. Small errors we make in the total energy from atoms far away won't affect that. So the forces will still come out. The error in the forces will almost certainly be proportional to the error in the energy per atom, not the error in the energy of the whole block of solid.
So Valentin Karasev asks, once you have an electron wave function and if you evaluate a reduced density matrix like electron density, is such evaluation very expensive?
Not particularly. I mean, variational Monte Carlo, and that's all this is, does that kind of thing quite routinely. So it's not particularly expensive. Obviously, if you go beyond the two-particle density matrix, you can't store it usually. But people have evaluated one and two-particle density matrices in variational Monte Carlo for a long time. So yes, it can be done. And one of the nice things about variational Monte Carlo relative to projector methods like diffusion Monte Carlo is that we can evaluate the expectation value of almost any operator quite straightforwardly, whereas in projector methods, operators that don't commute with the Hamiltonian are much harder to deal with and have bigger errors.
Fei Zhao asks, transition metal elements?
Can we do them? Oh, yeah. We have tried a little bit, actually. At the moment, we're doing full core calculations, so all the electrons are there. There are no pseudo-potentials or anything. And so when you're doing a transition metal, you have a huge energy range. Yeah, the energies the core electrons are bound with are enormous. And it is proving quite difficult. We can get results for individual atoms, but we're having trouble. There's a famous chemically difficult example called the chromium dimer chemists struggle with. And we're struggling with that at the moment as well. If we're prepared and content to use pseudo-potentials, which I am, although of course there are approximations there, I don't think transition metals will be particularly more difficult than the things we're doing now. So yes, in principle, we can do transition metals. Again, we've only tried a very small amount.
And there's a question from Edgar Landinez. Well, what about basis set effects? Can the neural network parameterization of the orbitals help to improve that?
So we don't use a basis set. Everything is done in real space. So our electrons are in positions R. So we have no basis set requirement in our method. So when we were comparing with things like coupled cluster, that's why we were very careful to extrapolate the coupled cluster results to the infinite basis set limit. So one of the great advantages of this kind of approach, this real space approach, is we're not stuck with a basis set in the way you are in almost all quantum chemistry methods and in DFT as well. We don't even discretize our real space. The electrons can go anywhere they want, so we sample it. So we just don't have a basis set.
Michael Cruz is asking if there's a publication of this work.
There is. I should probably also mention that some other people are doing similar things. I can't. Where's my talk gone? I think I lost it. Here it is. So there's work by other people. Herman and company did something very similar to us a little bit after, and Chu et al., who are from the Flatiron Institute in New York, did something really quite different, very different in flavor.
Could you make this full screen so people can see what we're doing?
Yeah, sure, easy. It's not that exciting. I didn't put our publication there. So our publication came out in Phys Rev Research in 2020, and if you ask me, I could email it around, or you could just find it, just search for my name. It's my only ever paper in Phys Rev Research. We were very ambitious, and we submitted it to ambitious journals, but quantum chemists, some of them were quite hostile. So in the end, we ended up after a long battle in Phys Rev Research. But it's got a lot of details in and many auxiliary extra material that you can read. So you can really learn most of what we do from there. And you can also look at the source code because it's available on GitHub. We started off, the first version was written in TensorFlow because that's Google's thing. But we've essentially rewritten it now in JAX, which is a much easier to use and nicer framework, I think. And the JAX code is also on GitHub, with the exception of the KFAC implementation, which we haven't got permission from to open source yet from the guy who wrote it. So you can look there, and you can look. The paper is full of details too. Yeah, Phys Rev Research 2020.
Okay. Well, thank you again for the lovely talk.
Thank you very much.
I hope
it was a pleasure. I still have no idea where the chat is, but that's fine. So thank you. One day perhaps I'll be able to come and visit. It would be much more fun. But anyway.
Yes, we look forward to having you when we can.
Okay. Thank you very much indeed.
Goodbye, everybody, and have a great rest of your Thursday.